Hello and welcome to Oslo in Norway, where we're about to find out some very exciting news. Who has won this year's Abel Prize? Awarded every year since 2003 by the Norwegian Academy of Science and Letters on behalf of the Ministry of Education. The Abel Prize rewards mathematicians whose work is of exceptional breadth and depth, and we're here in the Academy to find out the identity of this year's winner from the President of the Academy, Annalyn Eriksson. So let's find out who it is.
As the President of the Norwegian Academy of Science and Letters, it's my pleasure and privilege to announce the winner of the Abel Prize for 2025. The board of the Norwegian Academy of Science and Letters has decided to award the Abel Prize for 2025 to Masaki Kashiwara for his fundamental contribution to algebraic analysis and representation theory, in particular the development of the theory of D modules and the discovery of crystal bases.
The Abel Prize is a recognition of excellence in research and honors pioneering scientific achievements in the fields of mathematics. This year, we honor Professor Masaki Kashiwara from Research Institute for Mathematical Sciences at Kyoto University. Dear Professor Kashiwara, I would like to extend my warmest congratulations to you for your great achievements through your work on algebraic analysis and representation theory. The Abel Prize is a celebration of you as an outstanding mathematician and of the fields of mathematics as a whole. The world depends on research-based knowledge and expertise to understand and resolve our common challenges. By recognizing and honoring outstanding individuals that have made significant contributions to science, we hope the Abel Prize will inspire innovation, collaboration, and public appreciation for scientific advancements. On behalf of the Norwegian government, congratulations as the Abel Prize laureates for 2025. We look forward to welcoming you to Oslo and Norway in May.
The Abel Prize was established in 2002 by the Norwegian government to mark the 200th anniversary of the birth of Niels Henrik Abel, a Norwegian mathematician of prodigious talent. Before his untimely death at the age of 26, Abel made pioneering contributions to several fields of mathematics. Every year, the Abel Committee of internationally renowned mathematicians reviews the nominated candidates for the prize and recommends a winner to the Abel Board of the Norwegian Academy of Science and Letters. And here to tell us why Masaki Kashiwara was selected as this year's Abel Prize winner and to read the full citation is the chair of the Abel Committee, Helga Holden.
The Norwegian Academy of Science and Letters awards the Abel Prize 2025 to Masaki Kashiwara, Research Institute for Mathematical Science, Kyoto University, and Kyoto University Institute for Advanced Study, Japan, for his fundamental contributions to algebraic analysis and representation theory, in particular the development of the theory of D modules and the discovery of crystal bases. Symmetries are ubiquitous in mathematics and the physical world. Representation theory uses algebraic tools to investigate the ways in which a given symmetry can be expressed by linear transformations on vector spaces. Linear partial differential equations, on the other hand, are traditionally investigated using tools of analysis. Algebraic analysis, as initiated by the work of Mikio Sato, is a systematic study of these equations by algebraic means. Kashiwara has made groundbreaking contributions to this program, leading to surprising connections and spectacular results in representation theory. D modules provide an algebraic language for studying systems of linear partial differential equations. The 1970 master's thesis of Kashiwara develops the theory of analytic D modules, introducing the fundamental notion of characteristic variety and proving a vast generalization of the Cauchy-Kovalevskaya theorem. This demonstrates early on the power of algebraic methods in tackling problems of an analytic nature. This philosophy was taken further by Kashiwara when developing the microlocal analysis of sheaves in a prolific collaboration with Pierre Shapira. In a nutshell, microlocal analysis relates differential equations on manifolds to geometric objects on the cotangent bundle. Kashiwara, together with Takahiro Kawai and Sato, introduced various fundamental new concepts in this theory and clarified the geometric microlocal structure of systems of linear differential equations. Hilbert's 21st problem, often called the Riemann-Hilbert problem, asks for the existence of a linear differential equation on the Riemann sphere with regular singularities and with prescribed local monodromies. Pierre Deligne extended and solved this problem in higher dimensions. Kashiwara formulated and proved a vastly generalized Riemann-Hilbert correspondence, that is, the equivalence between regular holonomic D-modules and perverse sheaves. This result was obtained independently by Sogman-Mebkut. Quite recently, Kashiwara and Andrea Dognolo extended the Riemann-Hilbert correspondence to holonomic D-modules that are not necessarily regular. The Kastan-Lustig conjecture in representation theory can be viewed as connecting characters of representations to intersection cohomology groups. It was proved by Kashiwara together with Jean-Luc Brylinski in a striking application of the Riemann-Hilbert correspondence. An independent proof was obtained by Alexander Beilinson and Joseph Bernstein using different methods. Kashiwara and Toshiyuki Tanizaki later generalized the Kastan-Lustig conjecture to infinite-dimensional affine Lie algebras by developing D-module theory on an infinite-dimensional flag variety. Since then, D-module theory has become an indispensable tool and brought numerous new developments in representation theory, including in positive characteristic. Inspired by the study of solvable lattice models in mathematical physics, Vladimir Drinfeld and Mikio Jimbo independently formalized quantum groups in the late 80s. They are deformations of the enveloping algebra of complex, semi-simple or Kac-Moody Lie algebras. Kashiwara introduced the notion of crystal bases and proved the existence of crystal bases for integrable highest weight representations of quantum groups. The proof, which proceeds by an intricate induction process now known as the grand loop argument, is a tour de force that had not been much simplified ever since. Kashiwara also generalized crystal bases to global bases, which were independently discovered by George Lustig under the name canonical bases. This work can be thought of as a vast and fruitful generalization of the theory of Young diagrams and Young tableaux. Kashiwara is an exceptionally prolific mathematician with more than 70 collaborators. For over 50 years, he has reshaped and deeply enriched the fields of representation theory in its numerous incarnations and algebraic analysis. His work continues to be at the forefront of contemporary mathematics and to inspire generations of researchers.
Thank you, Helga. Now, that was quite difficult to understand for a non-mathematician. Would you be able to explain to us in slightly easier language why exactly Masaki Kashiwara won this year's Abel Prize?
Well, Timandra, this citation was meant for the mathematical community and is not easily accessible for a non-expert. But if we reduce it to the bare essentials, Kashiwara received the Abel Prize for his unique ability to combine techniques from geometry, analysis and algebra to reveal new and hitherto unknown connections between them.
Did Kashiwara's interest in mathematics start very young?
Yes, like many mathematicians and Abel laureates in particular, Kashiwara showed an early interest and talent in mathematics. So already as a kid he was fascinated by the Japanese game of Surukame-san, where you're given the number of legs of cranes as in birds and not machines, and turtles, and if you're given the total number of legs and heads of the cranes and the turtles, you are supposed to deduce how many cranes and turtles there are. So if the number is 6, there will be 1 turtle and 1 crane. But on a more serious note, Kashiwara developed one of his main tools already in his master's thesis at the age of 23. Here he invented the theory of D-modules. The thesis existed only as a handwritten document in Japanese until it was translated into English 25 years later.
Can you tell us something about D-modules and what they are?
So Kashiwara's advisor Sato had developed the theory of algebraic analysis to study linear partial differential equations. In analysis, derivatives are the result of a difficult limiting process, while in algebraic analysis, one focuses on algebraic properties of the derivatives after the limit is taken. In the hands of Kashiwara, D-modules became a very powerful tool to analyze algebraically some of the properties of linear partial differential equations.
Kashiwara has also done important work in representation theory. Can you tell us something about what that is?
Let's start with symmetries. Humans have always been fascinated by symmetries in art and nature. And of course, scientists try to analyze symmetries in crystals, snowflakes, as well as elementary particle physics. For mathematicians, they analyze symmetries using group theory, a theory that was introduced by Galois with connections all the way back to Abel. Groups can be very complicated, and in order to understand them, mathematicians have developed what is called representation theory, where the groups are represented by vector spaces and matrices, which are well understood and have been studied for a long time. And the problem may be simpler when they are analyzed in using representation theory. And Kashiwara has used representation theory throughout his career.
Kashiwara also worked on Hilbert's 21st problem. Can you tell us something about that?
Yeah, the German mathematician David Hilbert introduced in 1900 23 unsolved problems that have been guiding the development of mathematics in the 20th century. Hilbert's 21st problem deals with the existence of a solution of a differential equation with prescribed singularities on a Riemann sphere. Many mathematicians have worked on this problem for a long time, and Kashiwara proved a vastly generalized version of this. It was solved independently also by Mebkut, and recently Kashiwara has extended it further with joint work with Dagnolo.
It seems that Kashiwara has worked in a lot of different mathematical areas.
Yes, that's true. Kashiwara has shown a unique ability to combine different areas of mathematics. For instance, when he together with Brzezinski solved the famous Kastan-Lustig conjecture, they combined insight from geometry, analysis and algebra. The problem was solved at the same time by Beilinson and Bernstein.
From so much work, is there one result that you would particularly point to as important?
It is very difficult to select one problem out of a work of a mathematician who has published on the highest level for more than 50 years. It's like choosing a favorite child. But Kashiwara is very famous and greatly admired for his so-called grand loop argument, where the proof involves 14 simultaneous and interconnected induction arguments. And the proof has yet to be simplified considerably. This is a gem.
Thank you very much. Masaki Kashiwara is a builder of bridges between different fields of mathematics. Not just little bridges that join two ideas, but spectacular bridges that span mathematical worlds. Imagine a beautiful bridge that uses completely new construction techniques to join Norway with South America or Japan with Antarctica. Kashiwara connected the mathematical continents of algebra and analysis, and then the third mathematical continent of geometry with his original thinking. His ideas are not just beautiful and brilliant in themselves, they open up routes for many other mathematicians to explore new territories and solve new problems. At Tokyo University, with his supervisor and mentor Mikio Sato, Kashiwara pioneered algebraic analysis, applying the methods of algebra to the problems of analysis, the mathematics of how things change. Kashiwara's master's thesis, written when he was only 23, established the foundations of D-module theory as a way to algebraically analyse systems of linear partial differential equations. Differential equations describe how things change. Solving a linear differential equation can tell you not just how long it will take me to travel from A to B, but how fast I am moving at a particular point and whether I am speeding up or slowing down. Mathematicians like Kashiwara are less interested in solving the systems of equations and more interested in finding out about the properties a solution will have, if there even is a solution. Not every point in every differential equation has a definable solution. If a function is defined by 1 over x, then when x is 0, 1 over x would be infinity. A point like this is called a singularity. One long-standing problem in mathematics, Hilbert's 21st problem, sometimes called the Hilbert-Riemann correspondence, asks about the solutions of particular kinds of differential equations that have such singularities in the complex domain, where real numbers and imaginary numbers live together. On a complex manifold, the solutions around these singularities can behave very strangely indeed. Rather like following an arrow on a Möbius strip, you may follow the solution around the singularity back to where you started and find you're not where you started. A system of differential equations that has these strange points is called monodromic. The Riemann-Hilbert problem asked, can we say that a particular type of system of differential equations will always have this property of monodromy? And can we predict exactly where those points of singularity will appear? Using his D-module theory, Kashiwara was able to show that in any dimension there will always be a unique differential equation that fulfills the predicted requirements. Zogman Mebkut independently did this at the same time. In proving this Riemann-Hilbert correspondence, Kashiwara built a new bridge to the field of topology, relating D-modules to topological objects called sheaves. Kashiwara's work on sheaves, collaborating for over 50 years with Pierre Shapira, has also built a bridge to another mathematical region, representation theory. Representation theory uses algebra to study symmetry. An everyday object like a square tile has a finite number of symmetries. It can be rotated through a quarter or a half turn. It can be reflected along a line joining opposite corners or along a line joining the midpoint of opposite sides. But an object like a sphere has an infinite number of symmetries because it can be rotated on any axis and it can be reflected on any plane through the centre. And mathematical objects in abstract spaces with many more dimensions can combine symmetries in very complex ways. These relationships between symmetries can be expressed by a branch of algebra called group theory. Norwegian mathematician Sophus Lie invented Lie groups, which describe continuous groups of symmetries, like those of a sphere. Quantum groups were first developed to use Lie groups in statistical mechanics, but Kashiwara invented another completely new way to use them. Kashiwara's invention of crystal bases built another bridge, this time between representation theory and graph theory. Graph theory uses nodes or vertices connected by links or edges to model structures and systems. The mathematician Euler turned the famous Königsberg bridge problem into a graph. The problem asks, is there a route around the city of Königsberg, a real city on the Baltic Sea that's now called Kaliningrad, that crosses all 7 of its bridges exactly once and brings you back to your start? Euler used 4 nodes for the city's 2 islands and the 2 banks of the river, and 7 links for the 7 bridges. Using graph theory, Euler was able to show that there is no solution. You cannot return to the start without crossing a bridge more than once or missing a bridge out. Kashiwara's crystal basis turns the combined symmetries of a mathematical object described by a quantum group into a graph. All objects with the same combination of symmetries share the same graph. Crystal bases are now used throughout representation theory. The 2025 Abel Prize is awarded to Masaki Kashiwara for his work on D-modules and crystal bases in particular, but also for his wider contributions to algebraic analysis and representation theory and to mathematics in general. Pioneer, visionary, and builder of beautiful mathematical bridges. And now, direct from Kyoto in Japan, Professor Masaki Kashiwara. It's a
Hello.
great honor to meet you.
Yeah, thank you.
Congratulations on winning the Abel Prize. How are you feeling about winning the prize?
Yeah, that is a very incredible news. And I feel that my work of more than 50 years is well appreciated. Thank you very much.
In your work, you have collaborated with over 70 different people. Why is it so important to you to collaborate with others?
You have to know there are a lot of forms of collaborations. In one collaboration, someone asked some question and I knew an answer. So we wrote a joint paper. And in another case, someone has a good problem, but he doesn't know how to solve it. And he thought I should have a good tool to solve it. Or some collaborators, I spent a long time to study one subject. In this occasion, I would like to thank all my collaborators.
Many people say you have an unusual gift for finding different approaches and for seeing connections between different parts of mathematics. Where would you say that gift comes from?
I like to make a small calculations. It's like an experiment in other discipline like physics or engineering or so on. Very frequently, by those small calculations, it gives nothing. But perhaps it gives some confirmation of my belief, or very rarely that gives a good hint for the future work, or sometimes it gives unexpected things. So I think that is my way of doing mathematics.
What was it about mathematics that first captured your excitement, your interest? Do you remember?
The influence of my teacher, Professor Sato, Mikio Sato, is very strong. So I owe him very much. Sato is the initiator of algebraic analysis. When I started mathematics, I worked with him and my collaborator Takahiro Kawai for the construction of algebraic analysis. And I think most important thing that I learned from him is to create new things. I think before seeing him, I thought mathematics is already established and I have nothing to add or something like that. But I think he showed me that it's not true. And we can add new things and we can create new things.
I think in 50 years you have proved that you can create many new things. So in your master's thesis already, when you were just 23, you developed the idea of D modules, and that was fundamental in that new field of algebraic analysis. Did you realize at the time, when it was just a master's thesis, how important that would be?
I didn't really think about that. My thesis is just the beginning of the theory.
Do you have any advice for a young mathematics student today, maybe starting on their master's thesis?
I can repeat what I learned from Professor Sato. To create a new thing is important. Please create new things, even if it is very small.
I have heard you say in another interview that at school you encountered a problem called the Tsurukame-san. Is that right? Can you explain that for us?
Yeah. So that is what we learned at elementary school in the class of mathematics. So tsuru means crane, a bird, and kame means a turtle. Zan means calculation. So tsurukame-zan is literally, it means calculus of turtle and crane. And the problem is like that. You know the total number of cranes and turtles, and also the total number of legs. So you should know that crane has 2 legs and turtle has 4 legs. Much later we learned how powerful the algebra is.
So was that your first introduction to algebra?
That's true. And I looked at the encyclopedia to give those x and y and elementary algebra. And then I knew that we can solve the Tsurukawa very easily.
So already you were doing your own research to find a generalized solution.
Yeah.
How old were you then?
10 years old or something like that. Yeah.
You were a child prodigy. So it's been an honor and a pleasure to meet you, Kashiwara-san, and we look forward to welcoming you in Oslo in May.
Yeah, but I'm also looking forward to seeing you in Oslo.
Congratulations once again to Professor Kashiwara. And now, to tell us a little more about the Abel Prize, we are joined again by the President of the Norwegian Academy of Science and Letters, Anna Linn Eriksen. Why did the Academy set up the Abel Prize?
Well, actually, the Abel Prize was set up by the Norwegian government in 2002. And the Academy, our Academy, the Norwegian Academy of Science and Letters, is overseeing the work, the committees, the selection process, and the prize ceremony. And the purpose is, of course, to honor fantastic scholars and brilliant minds, but also to celebrate mathematics and to encourage and motivate mathematics for children and youth.
The Abel Prize is one of only a few major international prizes for mathematics. Is there anything that makes it special and different from all the others?
Well, it is exactly this inclusion of the young to stimulate children and youth to become interested in mathematics. The Abel Prize funds several projects that aim to motivate children, school children, for maths. When the prize is awarded in May, aspiring young mathematicians from several countries will be in attendance by invitation of the Academy, and perhaps a future Abel Prize laureate will be among them.
Now we know who the 2025 winner is. What happens next?
Well, we are all looking forward to the Abel Prize week in Oslo in May. It is going to be a fantastic celebration, and many thanks to the Abel Committee for their outstanding work. I welcome you all to the Abel Prize Award ceremony at the University Aula in Oslo on Tuesday 20th of May at 2 p.m. Norwegian time. Masaki Kashiwara will receive the Abel Prize from His Majesty King Harald V. There will also be a lecture in honor of the laureate at the University of Oslo on the Wednesday, 21st of May. Registration will soon be available through our website. You are most welcome to Oslo to celebrate this year's Abel laureate with us. Thank you.